Welcome to the Todd and Noah Show, taking the mystery out of electric motors. Once again, I have Noah Bethel, the Vice President of Product Development.
Hello from sunny Tampa, Florida. Broadcast from sunny Fort Myers.
Coming from sunny Fort Myers, and my name is Todd Gunderson, the Vice President of Sales and Marketing for PDMA Corporation. And Noah, this is a great podcast that we have. We've done tips regarding insulation. Now, this is case studies from the field, a forensic review of case studies that involve insulation.
It's like a CSI only for motors.
CSI for motors, which is actually exactly right. It is. It's a forensic review of how are these failures occurring and how can we help you stop some of these failures from occurring. So this first case study, this was probably the first time that we always would say Class B, Class F, Class H insulation. If you exceed it, potentially you reduce the life of the motor in half by 10 degrees Celsius. If you exceed it by 10 degrees Celsius, you reduce that motor in half. Well, here we go. This is kind of like the pictures are worth 1,000 words on this one.
Absolutely.
So this was a 125 horsepower DC motor. And come to find out, they did a thermography scan and they saw one motor looked hot, the other wasn't as hot.
Which is great to have comparisons, right? When you have comparison data, it's like another tool. And, you know, with the Sesame Street song, which one of these is not like the other?
One of these things is not like the other.
That's the song I remember hearing, yes.
One of these things are kind of the same. So here we have the picture of where the motor really looks overheated. It's bright yellow versus one that's maybe not as overheated. Almost a difference in temperature by 50 degrees Celsius. That's on the skin.
Yeah, that's in the external.
So internally, it's substantial.
Rise is going to be significant from external to internal. So yes, it's hot.
So the interesting thing about this, with this higher elevated thermography scans, when you go to do a resistance to ground check on it, guess what?
Doesn't always indicate the problem.
They're within spec.
Yeah, all too often.
They meet IEEE 43.
Yeah, we're seeing values of 11,000 meg.
11,000 meg, 10,000 meg. However, we don't just stop with resistance to ground, do we?
Indeed, we do not.
Phase resistance and we look at phase inductance. And that tells a different story. That is a substantial change in inductance and a substantial change in resistance when you look at those parameters.
Well, and that's one of the benefits of the AC, the high frequency inductance measurements that we're taking. When we send our signals into the motor with that, the higher frequency, the susceptibility or the ease of which it passes through the deteriorated insulation goes way up. And so that's a big deal.
So when they saw the change in the inductance and they saw the change in the resistance, they went and opened up the circuit. And when you look at the difference of the insulation when it's been overheated, it almost peels off.
Yes, yeah, the pictures are amazing, and the
it's
change,
embrittled.
It's heavily embrittled. It's almost like the insulation is not even there. You got a nice copper, good-looking cable to the left, and then on the right, literally you can see the bare copper showing through where it chipped off. It's significant.
And when you compare it to the regular insulation, there's no comparison there. So what they found was these motors had an undersized blower in them. And so obviously you need to fix that. You need to get the correct amount of airflow over that asset to take the heat off. Like you had said in one of these earlier podcasts that we were talking about, you have to the motors are not built to absorb the heat into the iron anymore. They're built to get out into the skin and then blown out of the motor.
Absolutely. Like, you think about the fan-cooled process of a normal motor. If the fan blades break or if something mechanically goes wrong with the fan, it's going to have a huge effect on the temperature. In this situation, it wasn't broken; it was just undersized. They weren't moving enough air to maintain the temperature. So, but the damage that resulted from that running in excess of the design is just incredible. And again, just to bring up the fact that the drop in inductance was huge.
It was massive, and that's because
huge.
When you look at inductance, a big component of that is turns squared. And when
Yes.
you lose turns because you've lost the insulation, now they're shorted to each other. So it means essentially you've lost turns out of the circuit.
Yeah,
That'll have a big change.
it did, and that was a big indication.
Almost tenfold.
Unfortunately, identifying this, was a little late for this motor because it's burned up, at this point, and they're going to have to replace
But
it.
the fortunate thing is they were able to say, okay, we burned up this one asset, but now we understand.
Stop the bleeding. Yes.
Stop the bleeding.
Yes.
Exactly.
Make sure the fan is the right size.
Make sure the fan's sized properly.
They've got a hard number that they can use as a baseline comparison and make that go away.
Yes. So this next drive is actually also, this next case study is also very interesting to us because it kind of incorporates kind of troubleshooting. How do you troubleshoot when you come across a situation? This case here, we've had a drive that has had multiple failures. Each failure costs about 40-some thousand per failure to fix. And we've had, 3 of these?
Someone's going to ask questions.
So at some point, wouldn't you think you have to?
Oh, you got to. Well, and this is I think we talked about it a few podcasts ago. It's like, years ago, the question was, is it the motor or is it the pump?
Yeah.
Right. And now, we've got technology to pretty quickly identify those two. Now the question is more, is it the motor or is it the drive?
Sure.
And in this situation, and we've also talked about, what's the easiest thing when you got a drive to a cable run to a motor? What is the easiest thing to replace when things are going south? The drive.
The drive is always going to be easiest.
You yank it out, put another one in, hook it up.
Or just a
push the start
component
button.
in the drive.
It
It's
could be
usually
that too.
misfiring something.
So this is happening 3 times at a cost of, $40,000.
45,000 plus all the trips.
Oh, yeah.
Process delays.
That's $150,000. So someone's finally asking questions and then looking deeper than just the drive.
Yeah. So what happened here was they said, okay, test your resistance to ground because that's what's causing all these issues. And that has to do with the zero reference.
It does. So here's what's interesting. You call the drive manufacturer and say, hey, I'm getting this type of performance. And why would the drive manufacturer ever suggest you check the ground? Well, you think, they're just pointing fingers at the other guy, right? But in reality, they have a real good reason to ask that. And in event of that, a drive is going to use the ground reference effectively, or the common, to know when it's time to fire to the next phase. Well, if the ground is erratic, it's going to misfire. It's not going to know when the right time to fire is. It's going to mess up the operation, basically. And so that's why they want you to check that. They want to verify, hey, is the ground wall insulation, is the ground reference, is everything good, so the drive can operate normally.
So they check the resistance to ground on a standard test, and they come up with 145 megohms.
Right. Important point on that is that's 145 corrected, right? So it's temperature corrected. And our system, what's interesting is 145 is above the minimum 100 meg IEEE recommendation, right? But this was newly refurbished. So you can understand that even though IEEE has standards for a reason, right? IEEE 43 says, hey, if it goes below 100 meg, it should be questionable for continued operation.
Right.
But no one was going to accept 145 meg coming out of a motor shop on a refurbishment, right? That needs to be understood. And so it raised questions immediately, like, why is a brand new refurbished? Well, then you start conquer and divide, right? You start looking at the cable run and see what's going on. That was the next approach.
So after the standard test and they found 145 corrected megohms, they did a polarization index test and saw not something that you would want to see. Looks like some breakdown.
this is classic moisture indications. Basically it rises and it's erratic. It kind of flattens out, but it's not a nice steady rise. It's heavy contamination or moisture is what we would have called on this.
And then we always recommend, since we tested it at the MCC, what's the next step? That is disconnect from
Test
the
the
motor.
motor
Test the cable circuit and the motor separately.
Right. And I'm seeing here the motor separately was measured at 3,400 meg, is corrected to 1,700, a much more acceptable post-refurbishment, right? These are numbers you'd expect to see.
100, that's 10 times.
Oh, yeah, it's huge. It's
10 times
1.7
increase.
gigohms corrected. It's 3.4 measured.
Versus 0.145.
It's a huge difference.
And the PI ended up at 12,000, 12 gigohms.
Right. Instead of flattening out around 300 to 400 meg, we're getting up to 14,000 megohms on the graph. A much better. So it relieves our concern about the motor, right? And it starts to focus back upstream.
It's power circuit. It's the cabling going to the power circuit. It's all
Absolutely.
of that comes into call. And so that's what I think the technician who was out in the field had said, listen, we think there's water intrusion somewhere. It could be in the conduit, right? That's water can filter out.
It finds a way.
It finds a way.
Absolutely finds a way.
It's very insidious and can get into a lot of different locations where you really don't want it to be. So that was their first thought is it's in the conduit. Let's go take apart some cabling. Let's see and pull that out and see that it's in the conduit.
And we would have been on board with this. We would have been we fully expect you're going to find insulation, moisture, and there's a lot of it. In fact, we were thinking.
So they go in and they pull it and they check the conduit and there's nothing in it. No water whatsoever.
Wah, wah, wah.
Water everywhere, not a drop to drink.
Dang. So imagine the disappointment. You're expecting to see something come out of there to indicate the values we were seeing, and it didn't happen.
So because when they were pulling the cables and the conduit, they found some abrasions on the lead wire jacket. So they're like, okay, let's do something while we're in here. Let's pull those cables out, and we'll still look. We'll still look to see if there's some water that we missed it somewhere. And while they were doing that and they were pulling the cable out and they were laying them against the wall or wherever they were storing them at, hanging them up against some hook or something like that, they started to see water drip out of the actual cable itself.
Right. So not in the conduit.
No.
But inside the insulation
in.
jacket itself, right, wicked up into the actual cables. And I guess
is that temperature over time where it gets to, where
probably
it could be where it heats
gravity
and then it cools.
For sure. I do think the heating and cooling was a big deal. Yeah. I think that what that does is it creates sort of a vacuum pull, and it was just for whatever reason it was pulling it into the cable. It was a great find because we were all like, man, there's got to be water someplace.
Yeah.
There's no way it could not be, and ended up it was in the cable, not in the conduit.
So once they found that issue, they were able to go back and say, thankfully, we thought it was water. We had a pretty good suspicion that it was water-related issues. And fortunately, they were able to find that.
And the post follow-up test was motor and cables together, which were almost as high as the motor by itself.
Right.
So it was a great
everything
recovery.
Now is running normal because we don't have a low resistance to ground, so that drive doesn't have a squirrely zero reference when it does its firing, and we can move on.
Someone deserves a bonus here. No more drive failures every sense.
No more. Yeah, I mean, that's expensive, $150,000.
Oh my gosh, yeah.
That's a tremendous amount of money being spent for something, just water.
An actual fault that doesn't go away.
So this next one is also going to focus on water. Water and electricity don't mix.
They don't mix.
They do not mix. We've got a low resistance to ground value, like 4 megohms. They did a polarization index test, the DA ratio of 1.04 PI of 1.15. That's below 2, right?
It is below. It's a problem. Yeah. It looks, for those of you who can't see it, basically it's a flat line. It charges up and it just flat lines for the rest of the 10 minutes.
Which would give us that 1 at the 60 second and then at the 600 second. It's essentially, like you said, a flat line. But what they found, once again, just water helps to create corrosion, and those test leads or the leads where these motors were at, or where these cables were at in the motor connection, or the I wasn't in the MCC, but it was in the motor connection box.
I think so, connection box.
Yeah, you saw heavy corrosion there.
Yeah, this is some severe deterioration. So this was
Even
obviously
up the cable jacket.
Yeah, they're cutting way up into it. They're trying to figure out, how far back into the cable from the lugs that the deterioration is occurring, and it's a lot. They're like, a foot into the cable and still severe water damage. So another situation where water goes where it's not supposed to.
So they replaced a portion of that cabling. I don't know if they replaced it all, because when they went to go back to do the September polarization index test, it was better, but it still wasn't great.
No,
but it was enough
great.
and this gets back to where plants have specific requirements that they say. You can have IEEE 43, when can you start a motor, when can you not start a motor. But in this case here, the plant said, good enough. The needs of the
mini.
The needs of the plant outweigh the needs of the technician saying,
right.
Hey, we should wait and stop.
Yeah, I think they definitely delayed catastrophic failure, and it's good that they fixed what they did. By no means are they completely out of the water.
We see here that the main problem was their conduit seal had failed and allowed the water to kind of go down the cabling and soak into the motor leads. So without a program of consistently going out and testing, you may not have found this.
Yeah, it was a good catch.
Yeah, it was a great catch. If you fail or this motor fails, it's potentially down for a day. That's $250,000.
That's somebody deserves a bonus.
Well, it's hard to say, or at least they earned their pay that week.
Amen.
Right?
Justification. Make sure you write it down, record it.
Write it down, record it. That's the best thing you can do for sure. Suncor Petrochem. Here we come up with, we have a nice case study here of a facility. Routine testing in the warehouse. While performing routine testing on critical motors that are stored in the on-site warehouse, they found a low RTG reading.
Wow. QA at its finest.
The thing is, they had surge capacitors in all of them, and that's what they suspected. Right?
And this can happen, right? Even if you're applying our test equipment and the surge capacitor, let's say it's designed to activate at 2,500 volts or 2,400 volts, and you exceed that, well, it's going to trip the surge capacitor, or the surge arrestor, I guess is another name for it, and we're going to see values around 5 meg. You're going to think it's failed, but it's just because it's shorting out and preventing a surge from doing damage. Happens all the time.
Yeah. And so when it does happen, you got to find out how did it get in there? And in this case here, it was a hole in the junction box, right? So the hole caused the water to get in, and you can see it in the standard test, right? You can see how it was, baseline was a certain amount, and then it just
we had measured values
lower.
of 36,000 megohms baseline that dropped to 3,700 meg. And, we always joke about when you open the connection box and there's a rust line halfway up on the connection box. Did that come from the manufacturer? I don't think so, right? So, it obviously moisture is settling in, and in this situation it was probably a bath. There was a hole in the top, it fills up, and then obviously it wasn't running out. It probably evaporated to some extent, but the damage is already there.
And you can see on a polarization index as well, it's just a straight up, straight over.
Dang, it actually dropped as low as 300 meg.
Yeah.
Down from 36,000. That's a flatline PI and the surface leakage. The surface leakage current dominates the absorption and the polarizing current and makes it for a 1.0.
Yeah. So holes found in the junction box, water intrusion.
Now, severe corrosion of all metal parts involved in the conductive, circuit. The lugs are rusted. The insulation is damaged. And that's a warehouse.
That's in the warehouse.
Wow.
Without a question. That's in the warehouse.
$100,000 a day loss if they installed that in.
Yeah. Right. Exactly.
Yeah. That's a big deal.
So follow-up tests show the fix, potential production loss, Could be $100,000 a day. So that's, once again, technician coming through, doing his due diligence, making sure that the information that he's collected is acted on. Not just, what the reds and the yellows that are given to you in the software are very valuable. It just says, hey, there's a change. Go look at it.
Right.
See why the change is. Now, this last one is an interesting case just because it's really more about adding excess grease to a bearing.
Well, you know what they say
can happen?
In the vibration industry? They say over-greasing kills more bearings than under-greasing. Obviously, if there's no grease, you're going to burn it up, right? But that's not the biggest killer, And so what's interesting is, how in motors, what's the biggest killer we talk about is heat, right? Well, if you have no grease in your bearing, ends up being a heat-related issue, right? But if you over-grease the bearing, well, now you puncture the seal and you're leaking it all over the windings, and so over-greasing is a bigger threat.
Right. So the data comes up. It's a current imbalance of 13%, impedance imbalance of 15%. Now, I've heard you speak on this before. If they're kind of 1-to-1.
Yeah, they're very close in this situation. And we say an equal percent imbalance of current and impedance, we focus on the power circuit.
Right. So that's more of a concern. Maybe it's not the stator circuit on this one.
Right.
But you also, I hear you say all the time, red is bad. And we have a resistive imbalance of 33%.
Oof.
Inductive imbalance of 10.
So we should quantify that. Red is bad. But every year you need to check the warning settings, right, in case the red value changed. Early on in the PDMA history, we had, inductive imbalance alarms.
Yeah.
And because different manufacturers were coming out with different things and some of the motors had different rotor designs and things causing elevated values, we adapted to, we increased our caution level and got rid of our severe level, and we want to wait until you get baseline data to determine what is severe. So, red is bad. And what'd you say, 33%?
In resistive imbalance.
Ooh, that's a lot.
That is a lot.
Yeah, 1% is a lot, is questionable. 33% is over the top.
Something's going on. So looking for a smooth drift towards infinity, when we look at a polarization index test, it's 1.36 for a PI index. It's kind of flat, but 84 gig, it's not that low. So
no, and this is a situation where I think during the insulation tip podcast we talked about how if all you're looking at is the 10 divided by the 1 for the polarization index, you're missing the profile, right?
Yeah.
And this value here, the PI is a 1.36. It's under, right? It's definitely under. But if everybody was looking at this just a few seconds before the 10-minute, it probably would have been 2. Right. And it's going
just
up, it's coming down. It's varying.
Right at the
it's
last
almost,
second.
Exactly. So it's this is a questionable PI.
Which again is why the profile, the actual graph is so important, because you can see physically what's happening to that insulation system.
Absolutely.
So then based on all of this, you can say, okay, we're going to pull this asset and we're going to see what the cause is for all these data points that are trending in the wrong direction. And they pull it and they find grease everywhere in the windings.
I don't think that came from the motor manufacturer.
No, I'm sure they didn't put that in there. But typically, there's, I don't want to say it was negligence or.
Well, this demands a C story.
Yeah.
So we were doing some testing at a well-known aerospace industry. Let's just call it that. And we were within a launch critical time frame, right? So by launch critical, I mean that once you got to within a few weeks of launch, everything became no touch. So we're doing some testing, and we've got these large air conditioner compressor motors that we're testing right now. You can imagine the importance of air conditioning, not for personal comfort like we're setting in today in the lovely recording studio, but the massive computer systems that are required to successfully launch things into space require a lot of cooling, right? So these air conditioning units were considered launch critical.
Yeah.
And literally we had to get authorization from the top dog even to even go into the building with these things, right? So they were complaining about one of them not operating properly. We clear the windings in terms of resistance and inductance, and everything looked good. But one of the motors had twice the capacitance value as the other motor. Capacitance is an AC, high frequency AC insulation look, right? Not a lot of voltage.
We use it as contamination
indicator, absolutely. So we're like, why is this one twice the value? There's something going on there, right? Resistively, it didn't look too bad, but it was twice the capacitance. So the DC resistance to ground looked pretty close, but twice the capacitance. And now the person that was there with us that had opened up the cabinet, knew nothing about electrical, but he said, "Well, I don't know about the electrical, but this motor sure uses a lot more oil." And I'm like, what do you mean it uses a lot more oil? Right. So ended up that, this was not a grease bearing. This is an oil bearing.
Yeah.
And as the sight glass goes down, they replace it. Well, ended up the whole interior of this motor was completely covered with oil because it was leaking through the bearing seal and been thrown into the stator windings. Didn't immediately go to ground, but very similar to what you're seeing here. Mm-hmm. A leaky bearing almost resulted in a failed launch. But everything went up okay.
Yeah.
They were able to identify it, get everything done, and move forward. So it was a good catch.
We've also had case studies come into us where there was a plant. It was a pulp and paper facility where one of the motors, there was two motors side by side. One motor in a 12-year time period had failed 7 times. The other motor failed twice over the 12-year time period. One motor was right below a washdown station where a dike had broke out, and so the water just kind of dripped on that motor with the oil and all the grime and grease and everything else that goes with that. Essentially, a puddle, the motor lived in a puddle for the whole, and so sometimes it doesn't take data. Sometimes, yes, data, of course, helps you. But sometimes it's just, you say this, I hear you say this all the time, use your senses. You have all these different, you have your nose, your eyes, mouth. Yeah, you have touch, feel. You have all of that. It's not, don't be opposed to using that as well. If you hear, you can hear rotors, like you had said earlier in one of the podcasts, where you're like, whoa, whoa, whoa,
right?
Whoa,
that modulating
whoa,
sound
modulating
can be heard.
Sound.
Absolutely.
You can hear that. You can feel it. You can smell, right? You can always smell when something's burning up.
Oh,
it
yeah.
doesn't.
Electrical insulation burning is a very distinct smell.
Now, you may not be able to see thermography or hot spots in there unless it's really bad. But
that's right.
It's just
on fire.
On fire. It's on fire.
But you can smell
fire.
it. You can definitely smell it.
Anyways, getting back to this case study, they essentially pulled it, found all that grease in there, over grease, like you brought up in the case study or the C story just before. Once they were able to clean all that out of there, the resistive imbalance went to 0 and the inductive imbalance went to 0.36.
That's really good. The cleaning process of something like that.
Was it cleaning or was it a rewind maybe? It doesn't say it was a rewind, but
man. I mean, the question is, that level of contamination,
cause that type of inductive imbalance and resistive imbalance.
I mean, first of all, for inductive imbalance to occur, it means we're leaking through the surface pretty easily.
Yeah.
I would want to rewind it. But I mean, again, if they're with a steam cleaning and a full, and the drying and everything, if they can clear it and the insulation hasn't aged as a result of the damage, good for them.
Mm-hmm. Power test shows market improvement, very little resistive or current imbalance and impedance imbalance. Insulation system went way up from 90 gig up to 216 gig.
That's a better looking.
Much better.
Absolutely.
Much better. So if it had failed in place, you're talking possibly 10 hours at a cost of $300,000 for the replacement of that. And so, but the actual cost was only $3,000. So 1% of that $300,000.
That's a good savings right there.
That's a huge savings. Unless you like to say he needs a raise.
Someone needs a bonus.
Someone needs a bonus. So that brings us to the conclusion of this case studies from the field, a forensic review of really insulation systems and power circuits and stators. It was kind of a combination of all of that.
Almost a potpourri of
Potpourri
case studies.
of case studies. As always, if you have something to share with us, we'd be more than happy to entertain that and bring it to the rest of our customers out there that enjoy watching our case studies. If not, I hope you enjoyed today's show, and we hope to see you again real soon. Until then, thank you, Noah, for sharing all your insight.
My pleasure.
And thank you to all of you for listening to us, and we hope you guys have a great day.